Today we're doing lesson 6.5, solving exponential equations. Now let's review a few things just to get our minds working again. When you see the word equation, what does an equation have that very much makes it an equation? A what? No? An equal sign. Very good. An equal sign. If you have a math problem and it has an equal sign, it is an equation. Now, at the beginning of this chapter, we learned about exponents. So someone give me an example of an entire power. 4 to the second power, 4 squared, 4 to the power of 2. There's a bunch of different ways we can read this. But this is a power. Now, which part of this power is considered the exponent? The 2 is the exponent, all right? So today our equations are going to have powers in them, and we are going to learn how to solve them. So look at your essential question. How can you solve an exponential equation graphically? Now, we are eventually going to grab our phones, open up Desmos, and solve these with graphs. But let's learn how to do it without a graph first. Now, an exponential equation is an equation in which a variable expression occurs as the exponent. Now, we need to break this apart because if you don't understand this definition, then you're not going to really understand what you're looking at. So let's go right here in the definition where it says a variable expression. Now, we already talked about an equation. An equation has an equal sign. What does an expression not have in it, though? If an equation has an equal sign, an expression does not have an equal sign. Okay, good. Now, what is a variable expression? Well, first you got to know what a variable is. So what's a variable? A letter, okay? So, variable expression. Is there anyone brave enough to tell me an example of a variable expression? Plus 4 is perfect. Because it has a variable, it has an operation, which is addition, and it has a number, which is 4. That is a variable expression. Anybody brave enough to give me another one? Z minus 2, I'll take it. That is also a variable expression. All right, now look at where it says these variable expressions are going to be in these problems. It says equations in which variable expressions occur as exponents. So these variable expressions are actually going to be your exponents. They're not going to be your bases. They're going to be your exponents. Now, there's 2 ways to solve these problems. Let's look at the first way. It says to set up and solve an exponential equation when bases are the same. Now, fill in that blank and highlight it because this is key. When the bases are the same, you drop the exponents down to create an equation and solve. So I want you to fill in the blank, highlight the word same, and I also want you to highlight where it says drop the exponents down, because if my bases are the same, I'm simply going to take the 2 exponents, drop them down, and create an equation that I can solve. So that's the easy way. But look at this second way. To set up and solve an exponential equation where bases are different. So what do we do if our bases are different? You must rewrite one or both sides of the equations so that the bases match. Then you can drop the exponents down to create equations and solve. So, fill in the blank, highlight the word different, highlight rewrite one or both sides. Now, that takes us into example 1 where it says solve the equation. And remember, I'm continuing to leave checking optional. Do I think it's a good option when you are taking a quiz or a test? Absolutely, because you can take your answer, plug it back in, and make sure you have the right answer. But it's optional for you, all right? So in letter A, it says 2 to the power of 2x equals 2 to the power of 6. So the first thing we're going to ask ourselves is, are our bases the same? So what are the bases in this problem? 2. So I want you to go ahead, either with a highlighter if you have one, or with your pencil. I want you to either highlight or circle the bases. Because this is how we start the problem, by asking ourselves, are the bases the same? Now, are the bases the same if they're both at 2? Yes. So what do our notes say we do if the bases are the same? Drop the exponents down. So Haley, what is the exponent on the left side of this problem? 2x equals, what's the exponent on the right side? 6. There's your equation that you're supposed to solve. Now this takes us all the way back to chapter 1. This is a one-step simple equation. How do I solve for x? Divide both sides by 2. So what does x equal? There you go. And you're done. So drop the exponents down. That means I've taken those exponents and I'm writing them now as a normal-sized equation. and I'm solving that equation for x. Now, remember I said you could check. It was optional. Let's go ahead and check just so I can show you what that looks like. If I plug 3 back up into that first exponent, what is 2 times 3? 6. Everybody, what's 2 times 3? 6. So, is 2 to the 6th power equal to 2 to the 6th power? Yes. So we know we have the right answer because it checks out. Now look at letter B. Okay, first question. What are the bases in our problem and are they the same? 5 and 5. So, yes, they're the same. Since the bases are the same, what did you guys do next? Dropped those exponents and created an equation that you could solve. So 2x equals x plus 1. Now, you have to think back to don't call me after midnight. This is a multi-step equation. This is not a simple one-step equation anymore. So, what does the D stand for in don't? Distribute. Was the distributive property in this problem? No. Call. What's the C stand for? Combine like terms on the same side of the equal sign. Were there any like terms to combine? What does the N stand for? Move the variable. Is there a variable on both sides? Yes. So how do we move, or which one do we move? Subtract x. Now, technically it wouldn't matter, but we're always trying to get our variable to the left side of the problem if we can. So we're subtracting x. So what is 2x minus 1x? Because remember, there's an understood 1 right there. So this is 1x or x, and it equals 1. So again, you have solved for x. You can plug it in if you want. 2 times 1 is 2, which gives you 5 squared. On the other side, what's 1 plus 1? 2. So you get 5 squared on the other side as well, and you know you've done it correctly. In letter C, are the bases the same? Yes, what are the bases in letter C? 7 and 7. Okay, so Seth, since the bases were the same, what did you guys do first?
We got rid of them.
And what did you write down?
3x plus 5 equals x plus 1.
All right, you brought those exponents down and you got 3x plus 5 equals x plus 1. All right, again, don't call me after midnight. It says we have to move what first, or do what first? The variable. So which variable did you choose to move? The x. Good. So you subtract x from both sides. What is 3x minus x? 2x. Bring down what we have not used, which is plus 5 equals 1. All right, Timothy, what did you guys do next? What'd you do? Okay, how'd you move the 5 to the other side? You subtracted it, so 2x equaled what? -4. And then Trayon, how'd you guys finish this one? Divide both sides by 2. So what did x equal? -2. Now, when we move to letter D, E, and F, you probably noticed right off the bat, what is different about D, E, and F? The bases are no longer the same. All right, so what do we do when the bases are not the same? Well, the first thing we do is we identify that the bases aren't the same. Then we identify the larger base. So, Jeremiah, what are the bases in letter D? 4 and 256. So, Jeremiah, of those two bases, which one is the largest? 256. So, take your highlighter if you have it, or take your pencil and circle 256. Okay, because this is the one that we are going to change. If we are able to change the largest base to the smallest base, then we only have to change one side of the equation. Unfortunately, if the larger number cannot be changed to the smaller number, then we're going to have to change both sides of the equation. But we're always going to start first and see, can we change the larger base to the smaller base? Which means I want to know if there is 4 to some power that will give me 256. So either do some math in your head or grab your calculator and play around with some different numbers. 4 to the first, obviously, is not 256. What's 4 to the second? 16, so that won't work. So play around and see if 4 to some power will give you 256. 4 to the fourth power will give us 256. So we are changing the larger base to 4 to the fourth power. Now, since we were able to change the larger base to the smaller base, that means we can just bring down the other side of the equation and we can bring down the equal sign. Now, are our bases the same? Yes, so we're right back to where we were for A, B, and C, which means we do what with the exponents? Drop them down and write an equation. Now, this one's finished, solved, X is already isolated, so you have nothing else to do but box in that answer. Now, let's move on to E. I'll take questions in just a minute, but let's keep moving on to E. And tell me, what are the bases in letter E right now? 9 and 3. So again, highlight them or circle them if you don't have a highlighter. Which one is larger? 9 is larger. So we are going to see if we can change 9 to 3, because 3 is our smaller base. Is there a power that we can raise 3 to and get the number 9? 3 to the second. Now, you'll notice something. If you look back at 256, it was raised to an understood power of what?
1.
Of 1. So really, all we had to do was completely rewrite it and make it 4 to the 4th, and there wasn't really much to think about. But what happens when you look at letter E? 9 already had an exponent. So here's what we're going to do. We're going to take the new power, and we're going to put it in parentheses so that we can then bring down the exponent that was already there. And we're going to bring down 3 to the power of x minus 6 on the other side. So we've changed our bases, but we're not quite to the point where we can say, are the bases the same? All right, because look right here. We have 3 squared, and that 3 squared is raised to another power of 2x. So you've got to go back in your mind to before Christmas, before the midterm, where we learned the power of a power rule. What are we supposed to do to the exponents when one power is raised to another power? Multiply. So this is actually going to be 3 to the power of what? 4x. And then it equals 3 to the power of x minus 6. So I would highlight, right here where I highlighted, I would highlight that in my notes so that it stands out. Okay, I don't want to drop anything down until I've done all the work that I can possibly do with those exponents. Now, are my bases the same? Yep. So what do I do next? Exponents, and what do I get, Haley?
4x equals x minus 6.
There you go. And now we begin to solve the equation. Seth, what do you do first to solve this equation? Subtract x from both sides. What's 4x minus x? Anyone? What's 4x minus x? 3x, and it equals? 4x minus x is 3x. It equals negative 6. Divide both sides by 3, and x equals negative 2. Now, moving on to letter F. First of all, what are the bases in this problem? 1/3 and 27. So the question is, which base is larger? 27. Now, is there anybody in here that is interested in changing 27 to a base of 1/3? Okay, so let me help you out. Let's get rid of the fraction first. We know how to get rid of the fraction. So here's what I want you to do in your notes. Draw yourself a little arrow, and I want you to make yourself the little note, change first. Because if we can get rid of the fraction first, then it's going to make our lives much simpler. Now let's pull this fraction over to the side and let's review something we learned again before Christmas. We can move a power from either the numerator down to the denominator or the denominator up into the numerator. And that's how we're going to get rid of this fraction. We need to move 3 up into the numerator, because if we do that, then the fraction is gone. However, 3 is raised to what power at this moment?
1.
To the first. And what did we learn happens when we move a power either up into the numerator or down into the denominator? What happens to it? Sign of the exponent changes. So when I move 3 to the power of 1 up into the numerator, it becomes 3 to the power of negative 1. And remember, we can keep the 1 and multiply by 1 if we want, but it's not going to change the fact that we have 3 to the power of negative 1. So let's put that into the problem. And again, we're going to put it in parentheses because there was already an exponent of x minus 1 right there. Now, can we change 27 to 3? Is that more doable? Yes. So 3 to what power gives me the 27 that is there? 3 to the power of 3. Now again, before we drop anything down, let's make sure there's no work to do in the exponents. We have right here -1, and it's raised to the power of x minus 1. So what am I supposed to do with those exponents? Multiply. But be careful, because that is a -1 that needs to be multiplied by what we call a binomial. So what do we actually have to do here with the -1 times the x minus 1? Does anyone know? All right. What if I dropped it down and said -1 times x minus 1? What if I wrote it like this? Would you have any trouble knowing what to do? No. What would we do right here? The distributive property. Okay? So this is the distributive property just up where my exponents are. So this is what I want you to do in your notes. I want you to draw yourself the arrows. Okay? Again, I would not require this in homework or tests or quizzes, but at least for your notes, so that when you look back, you know what you did. Draw those arrows. So this actually becomes 3 to the power of what? Negative x plus 1. Because -1 times x is negative x, and -1 times -1 is a positive 1. And then, of course, we're going to bring down equals 3 to the power of 3. Now are my bases the same? Yes. So I can drop them down, and what's the equation that I write? Negative x plus 1 equals 3. And how would I solve this equation? Subtract 1 from both sides. So negative x equals 2. And how would I finish this one off? I would divide both sides, because there's an understood 1. I would divide both sides by -1. So x equals? -2. Now, let me show you a shortcut for those of you who like shortcuts. When the coefficient of your variable at any point in any problem, if the coefficient of your variable is a -1, and this only works if the coefficient of your variable is a -1, you can actually just change the sign on both sides of the equation. You say, what do you mean? Well, if we went back to negative x equals 2, and we recognize that there is a -1 in front of that x, I can just change the sign on both sides of the equation. So negative x would become a, what kind of x? Positive x. And positive 2 would become a -2. And you could skip this step right here. You say, Ms. Johnson, you lost me. It's fine. If I lost you, don't worry about it. Just divide both sides by -1. Okay, but some of you like shortcuts. What if I gave you -2y equals 4? Would the shortcut work there? No, because the coefficient is a -2. But what if I said -y equals -4? Would the shortcut work there? Yeah, because this is an understood 1, so there's a -1. So what would the answer to that question be without having to divide both sides by -1? It would be positive y equals positive 4. You would just change the sign on both sides. Okay, so that's just a shortcut for those of you that look for shortcuts. Again, if you don't understand what I just said, you just keep dividing both sides by -1. Now, I want you to go grab your phones, I want you to open Desmos, and I want you to lay them flat on your desk. Now, in example 2, it asks us to use Desmos to solve the equation. Now, you're going to see some very familiar things here because we have done this before, but make sure you are paying attention and you are highlighting certain things. It says, set each side equal to y and plug both equations into Desmos. So you're not going to go to Desmos and plug in exactly what you see. You're going to have to start by setting each side of the equation equal to y. So that means y equals 4 to the power of x minus 3 is one equation, and y equals x plus 2 is your other equation. So make sure you set both sides equal to y, then you're plugging two separate equations into Desmos. All right, now if you remember, we're going to put in y equals 4. But if you hit the keyboard button, remember, there's an a squared option and there's an a to the power of b. Well, we're not trying to square this, so we don't want to hit that button. We actually want to hit a to the power of b, which will allow us to raise this to any power that we want. Now watch what happens if I just start typing. If I do x minus 3, look what happens. It keeps x as the exponent, but then it drops -3 down as a constant, and that's not what we want to do. So here's what you have to keep in mind. When you're inserting an exponent that has more than one thing, more than one number, more than one variable, you've got to keep the exponent in parentheses. So we would back this up and we would actually hit the parenthesis button on our keyboard, and then we would type in the x minus 3, and of course we would close the parentheses. All right, now what kind of problem is this? What kind of shape is this? We learned this again before Christmas. This is an exponential function. Now remember, when it's curved like this, how many points have I asked you to identify and plot on your paper? 2. So let's find 2 exact points. And if you remember before Christmas, most of these graphs run along the x-axis, but if you were to zoom in close enough, you would see this one eventually lays on the axis. However, I still would not choose points down here. I would go choose exact points on the curve. So give me some exact points that you see on this graph. 3, 1. All right, remember, we can plug in the points. A little bit better than that. Plug in the points, and then we can actually ask it to label it so we can make sure it is on the graph. And it is. So give me one more point on the graph. 4, 4. Again, let's label it. And it is exact. All right? So go ahead, plot your points, label them, and draw your line through it. Make sure you get your arrows on both ends. Now, we've got a second equation that we have to plug in. It was y equals, I believe, x plus 2. Correct me if I'm wrong. Was it x plus 2? All right, now what kind of a function is this? What kind of a graph or shape is this? This is a line, which makes it a linear function. And how many points have I asked you to give me when you're graphing a line? 3. Again, give me exact points. What have we got?
0, 2.
All right. I heard 0, 2. So we plot it and label it. It is on the line. Give me another one. All right. 1, 3.
2, 4.
Hold on. Let me check 1, 3. All right. 1, 3. And what was the other one? 2, 4. How about 1 under?
-2, 0.
All right. But remember, we talked about you can give me -2, 0, but if you actually put your finger on this and you click on it on your graph, look what the point is actually. So you got to be careful. All right. You got to be careful on that one. All right. -1, 1 is a good one. All right. Awesome. So plot your 3 points, label your 3 points, and draw your line. Now, you do need to draw the line long enough to intersect the other graph, because the second thing it tells you underneath the directions is to find the points of intersection and which variable is going to be your answer or your solution. X coordinate is your answer. You say, why is my X coordinate my answer and not the entire ordered pair? Because look at your original problem. What's the only variable that was in your original problem? So that's the only variable I need to solve for. They don't need y, because y wasn't in the original problem. Now, you say, Ms. Johnson, we didn't mark the points of intersection as points on our graphs. And that's okay. Why did we not do that? Look at this point of intersection. Why would we not choose that as one of the points that we graph? It is not an exact point. Look at what happens when I click on it. When I double click on it, it's 4.331, 6.331. And remember what I told you down here? If you click on this one, even though it looks like -2, 0, it's actually -1.999 and 0.001. So while we're not going to plot them, we still need to write them down. So go ahead and take the 2 points of intersection and write them down on your paper. You can write them beside the equations. You can write them underneath them. It doesn't really matter. Just write them down on your paper. The only thing left for us to do is to actually write down and identify our final answer. You've got those points of intersections written down. And again, we need which coordinate for our final answer?
X.
The x. Now notice how I'm going to write this down. I'm going to write this down as x is approximately. I'm not going to use an equal sign because these are not exact numbers. These are approximations. So x is approximately, and you'll notice down here that I went ahead and I rounded that -1.99. What did it round to?
-2.
-2. All right, so x is approximately -2. and x is approximately, here's my other point of intersection. You say, well, Ms. Johnson, how do I know what to round to? Let me just tell you, get in the habit of rounding 2 decimal places. Unless the directions tell you otherwise, we will always round to 2 decimal places. So what is the other x approximately equal to? 4.33. Because right here, after the second 3, there's a 1, which tells us that the 3 stays a 3. All right, that's just the basic rules of rounding. So we're rounding to 2 decimal places, which gives us 4.33. And this is our final answer. And that's lesson 6.5.